Ramanathan, do you remember how many classes we have for bandit algorithms? 4? You will try, okay, fine. Because the rate at which I am going, I will probably need one more class just to finish the 2 proofs I wanted to do today. So which would mean that I would need one more extra class for finishing all of bandits. Did we do 4 classes last year? 6. Huh? Yeah, I think we did it. We have even had a visiting faculty give a talk.
Ask Ramanand.
Okay. We have 4. Oh, good, fine. Then I'm not too bad off. Okay. So instead of writing the cumbersome 2 ln n by s all over, right? So I am defining that as Cns. Okay. Then if I write Cn minus 1 s, it's ln of n minus 1 divided by s, and then I can do Cn comma s plus 1, so on and so forth. Right? You can, it's just like a function, just substitute it, that make my life a little easier. Right. So the goal now, as I mentioned earlier, is to upper bound this expectation. Right. So I will never play a suboptimal arm more than this many times. Okay, that is essentially what we are trying to show. Okay. So one other notation, I will just adopt the notation used in the proof here, even though we introduced a different notation in the previous class for the same thing. Okay, it makes it a little easier for me. This notation indicates denotes a random variable corresponding to that indicator, right. So this is a random variable whose value is 1 if it equal to I, whose value is 0 if it is equal to not equal to I. Okay. So whatever is this, I will put in some kind of events here later, right. So if it equal to I, then what does it mean? It means that okay, fine. I apologize for the confusion. This yeah. So when I say in equal to I, okay, it means that at time n I played arm I, right. So if this, the whole expression within curly braces will be 1 if at time n I played arm I, it will be 0 if at time n I played some other arm, not I. Okay. So there are a couple of things which you can observe about this. So at any instant I, in equal to I will be 1 for some I, okay, for everything else it will be 0, right, because at every time instant I can play only one arm, and at every time instance I will play at least one arm. Okay, so it will be 1 for one of the arms, for everything else it will be 0. Okay. So this yeah, the paper is not really the most accessible of papers out there, right. So if you are going to read it on your own, you will have to do some work. Okay. So things are not, I mean, they just assume that you are all really smart people reading the paper. So so some of the gaps you will have to fill in yourselves, right. I am just doing one of the proofs in the paper. So if you want to read the rest of the paper and understand all the theorems and all the algorithms that they describe in the paper, so you will need to do some additional work. Okay. So L is some arbitrary positive integer. So I start off by saying this. I don't want to use t as a running variable. Okay. So, the number of times I have played arm I up till the nth instant will be 1, which I get from the initialization, plus k plus 1, because obviously I could not have played that arm again in the first k times, right. In the first k times I will play each arm only once, right. So, arm I also I would have played once. So, in the first k trials the summation will be just 1. So, I just have that 1 there, and from the k plus 1th trial till the nth trial I add the number of times this variable is 1. What does it mean? The number of times I have taken arm I, right. So, Im will be Im equal to I will be 1 whenever I take arm I. So, I just sum this up so that the number of times I played arm I is what I get, right. Is that fine? This expression is fine. Okay, this is the only directly intuitive part that we have here. So, now after this whatever you do, or these are all standard tricks that people play to bound random variables. Okay. So, to actually tell you about the general techniques for all of this, I recommend you take the ATTOC course, because about a third of the course is all about how to do proofs like this, right. So, how many of you have done ATTOC already? Advanced techniques in theoretical computer science, theory of computation. Okay, that is a course that Jailal Sharma teaches in the CS department. So, it is very relevant to a lot of ML researchers, because lot of machine learning has become like randomized algorithms, right. So, if the people teach you how to analyze randomized algorithms, you can take the same ideas and use them in analyzing machine learning algorithms as well. So, a lot of the tools that are developed there are useful here, and many of the things that we do here, right, essentially have their roots in the kind of analysis that people do for randomized algorithms. Okay. Anyway, so we will start off by doing that. So, I have an arbitrary number L. Okay. I say that, okay, fine, let us assume that I have played the arm L times. Okay. Then let us start counting. Right. So, assuming that up till the m minus 1th step, okay, I have L or greater than L, right, only then I will count the arm pull. So, at some point I have discovered that I have pulled arm I. Okay. So, should I add it to my count or not? What I do, I will go ahead and look at the cumulative count so far. If the cumulative count is L or higher, I add it to my count. If it is below L, I do not add it to my count, because I am anyway starting my count from L. Okay. So, this is slightly different way of doing that. This is saying that I will start the count from some arbitrary number, given that I have taken that arbitrary number already, right. So, later on we will essentially, now we are going to bound this expression, assuming that at least L times I have taken the arm, right, and then we will derive a bound for L, so that we get whatever probability we want. Okay. So, that is the idea behind doing this. So, this I can now derive a bound for this, assuming I have done at least L times, right. Then I will go back and find what is that value of L, so that I get whatever probabilities I want, right, whatever guarantees I want, I will go and find that L. Okay. That is essentially what we are going to do here. Okay. I just need more notation here to write this, but let me try this anyway. So, when am I going to take arm I? Right? When will I take arm I? When arm I has the highest, where is this thing? Right? When arm I has the highest value for this quantity, right? When will I take arm I? When that has the highest value for this quantity among all the arms. Specifically, I will take arm I only when q plus c, so that root term is now c, right? Right, that root term there is what I have written here as c. So, I will take arm I only when q plus that c term is greater than q of a star plus the c term corresponding to a star.
So this will be a larger set than
Yes, that is why I have my lesser than or equal to here. See, specifically this should be true, right? In fact, it has to be larger than everything else, right? But at least it has to be larger than a star, correct? So, it has to be larger than every other action, but like he rightly pointed out, so this is a larger set than when I will actually be taking the action, but that is okay because I am only trying to upper bound it, right? I am not trying to give you an exact number, because trying to give you an exact number makes it too involved, right? I am just trying to give an upper bound. So, I am saying very specifically, I am looking at the best arm, I am saying that this should be better than the best arm at least, right. So, anything else we need to have? Well, you still need to have this, right, that condition is also there. So, I will put that condition back in. And what does this curly bracket mean? It's the curly bracket is a random variable that indicates that will have a value of 1 when the expression within the curly bracket is true, it will have a value of 0 when the expression within the curly brackets is false. So, essentially this summation counts how many times this inequality becomes true after I has been taken L times, right. So, that is what we did here, right. So, this counting is whatever we are doing here is after L times I has been taken, because L I have added here as a count. So, likewise I am counting the number of times this inequality becomes true after I has been taken L times. So, this is essentially what I have so far, right. Where?
the last one.
Here,
The entire
this entire thing, that is a seat, take it here. And there is another seat vacant here if you want to move as well. You can see everything. You guys are all fine, right? No, you don't want to complain, because I will tell you there is a whole row vacant here. No, can't you see what I have written, or don't you understand what I have written? Well, subscripts become small, right? If I write them large, then it becomes confusing. So, that is Cm minus 1, for people who can't read it, I am reading it out, that Cm minus 1 comma T A star of m minus 1, that is basically the number of times I have played A star up till the m minus 1 point, right. Note that I do not have to know this because I do not know what is A star, right. This is just the that, but you know that there exists a star, right, and I know that my I has to have a better whatever into that quantity than A star, right. So it is just that, right. I do not know, I do not need to know which is A star, okay, just do not get confused by the fact that I am using A star in the proof, right. Did you get that, that C m minus 1 comma T A star m minus 1, and this is C m minus 1 comma T I of m minus 1.
So is the A star true, like the true best action or the previous best?
No, A star is the true best action which you do not know anything about, right, because for regret we have to compare against the true best action, right. So we are comparing against the true best action now, right. Okay, so far so good, people can, if people who couldn't see heard me, right, and people understand what is going on, right. So now we will, I am shifting over here. My God, writing one line I am talking for 10 minutes, man. I really need to have an additional index for the Q function for us to say these things, right. What I wrote there is m minus 1. So the Q function at step m minus 1, okay. I really need that additional thing because Q keeps changing over time, right. So I need to know at what stage I am talking about the Q function. So at that point I am talking about the Q function at the m minus 1th stage, right. Remember that the Q function at the m minus 1th stage can be the same as the Q function at the mth stage if I had not taken the action previously, right. In the m minus 1th stage, if I am not taking action A or action I, then at the mth stage also the Q function of action I will be the same, it would not have changed, right. It's just you have to be careful about how you interpret the index, and I hope I also do not mess it up when I do these things here. No, so we do need a different interpretation for, and I do need an additional notation, I apologize for that. Because we need to, what we need to insert into this bound here is the number of times I have taken A star for so far, right. What I need to insert into this bound is the number of times I have taken A star so far, which is T A star m minus 1, right, and so it will become a little cumbersome. No, this can be, yes, this will be T A star or yes, okay, fine, so I can get away with that. So this is a little weird expression. So what I am saying here is, okay, take the minimum of this expression, okay, over all time instants 0 to m, take the maximum of this expression, right, for all time instants L to m, okay, and look at the number of times one will be higher than the other, right. This will be an over count of that event, that is clear, right. And here I am talking about this quantity being higher than this quantity at that particular instant, right. I am talking about some time m minus 1 where the quantity for A star was lesser than the quantity for I, talking about some time instant m minus 1 at which this happened. Here what I am talking about, okay, at a time m minus 1, right, I look at all the A star values I have had in the previous time steps, okay, I will take the least of that, right, and I will take all the I values, qi values I have had in the previous time steps, I will take the max of that, okay. If the max of this is greater than the min of that, then I will count that as 1, right. So can you convince yourself that that event will certainly be counted, right, because at that instant the value is already greater, so obviously the max will be greater than the min, right. So if this is not the min, right, the min should be lesser than this, and if this is not the max, then the max should be greater than this. So if this value is greater than this value, then some quantity greater than this value will certainly be greater than some quantity lesser than this value, right, you can see that, right. So this is just a over count of that event, right. Why am I writing this over count? Because it makes it easier for me to, oh sorry, now that is the event, right, the curly brackets makes it easier for me to write a expression. Yeah, was it? One sec, I will come, let me finish. Yeah, 0 less than s less than m, L less than or equal to Si less than or, because L, because I have that condition there, right, I have to have taken this at least L times. So the first L times what happens, I do not worry, so I will remove that, right. So only after that I am worried about, but this will be an over count, okay, this will be an over count of that. It's a little tricky here. So no, the proof actually assumes that at this point, okay, I have taken this at least s times, not t s star s times, okay. This is mainly because this is a notation translation problem, but we will see, we will work with this and then I will probably adjust the results later, right. But if you are reading the proof, I am just telling you there is a mismatch in the notation that we have used so far, okay. But this is a neat trick that we have now done, right. We have taken rid of all the min, max and everything, right. So what are we doing here? So assume that the min occurs at some index, right. Let's call that index I do not know, p1, well, assume that the max occurs at some index, say p2, right. So now what I am doing here is I am summing over all possible indices for A star and I am summing over all possible indices for I, correct. So the combination P1 P2 will occur somewhere because I am summing over all possible indices, right. At some point I would have used P1 for S and P2 for Si, correct, because I am summing over all possible indices, right. So what was P1? P1 was the one for which this minimum was achieved, P2 was the one for which this maximum was achieved. So when I am summing over S, at some point S will have P1, at some point Si will have P2, right. At that point this expression will surely be true because I know from the min and max argument that we had earlier that will be true. So I will certainly be counting this, right. I will be over counting, I will be counting other things also, but I will certainly be counting this. So essentially so far we have not lost anything, we are essentially still maintaining it as an upper bound, okay. So we started off with this event, right. Now we have done a lot of simplifications, I have kept loosening the bound, this was a strict equality, there was nothing here, right. This was strict equality, no approximation here. So from there at every step I am essentially counting a larger and larger event. Now the thing is I have come to a point where I have a simple enough expression, right, that I can try to bound directly now, okay. So you can start thinking, this kind of should lead you to the Chernoff-Hofting bound. I can use the bound Chernoff-Hofting bound to try and bound this expression. This is a simple enough expression, okay. Okay. So if this is true, okay, if this is true, when can this happen? So my claim is this can be true if one of several conditions hold, right. So this can be true if this can be true if I am either grossly underestimating my optimal actions value, right. So this is my optimal actions estimate now, this is the true value, right. So the true value minus the confidence bound or the other way around, think about it, right. This QS A star plus the confidence bound is less than the true value. That means I am grossly underestimating the true value, that is one thing, right. So that could be one condition under which this could be true. What could be another condition? You are grossly overestimating the ith value, you are getting it. So either I have to make a big mistake for my Q star A star or I have to make a big mistake the other way for my I, right. You see that, right. So I have to either come very down from a true Q star value, I mean Q star A star, or I have to be much above my normal value, otherwise this is not going to happen, right. So second condition is okay, or when can it happen without me grossly overestimating or underestimating it? When the two values are close, right. If the two values, the A star value and the I value are close to each other, then I really do not have to grossly underestimate these things. So it is possible that I still could make errors, right. So essentially the other condition is right. So I have my twice my, I take the confidence interval, right. So I have a confidence interval, I add here, I will have a confidence interval, I will add from that side, right. So right, so I will add a confidence interval, right. So I am taking twice the confidence interval from my lower value, right. From the lower value I take twice the confidence interval, and if the upper value that is optimal actions value lies within that, right, then I can make a mistake without making a gross error also, right. Essentially I am saying that these two are close together, right, and close is a relative term. Close is defined in terms of the current uncertainty I have, right, because this is going to change every time I take an action, this is going to become smaller and smaller, right. So at the beginning of the learning this can be fairly large, so I can still make a mistake, right, even if the means are slightly far apart, right. So do you see the three conditions? One of these at least will have to be satisfied for this event to become true.
Can you explain the second one?
The second one says, when second one is easy, man. So the first one says, okay, I have my Q of A star and I have my confidence bound, this is the first one, okay, and the true Q star A star is there, okay, that means I have grossly underestimated my Q star is, this is one condition. So the second condition says, this is Q of I, right, and this is Q star of I. So grossly overestimated my Q star of I. So that is essentially what the second condition says. So this is Qi is greater than Q star I plus the confidence bound. So this is the confidence bound. So Q star I plus this confidence bound will be only till here, right, but Qi is greater than that.
So is that third one as a result from the first second, or
What's that?
is the third condition a result of the first second?
No, it's yet another condition that can hold, right. When both of these do not hold also, I could still be making a mistake, right, this could still be one if the true means are not far apart with respect to this error bar I have. See, basically what I am saying is a true Q star could be somewhere here, right, but I still can make a mistake because it is too close. Should probably draw all these pictures and put it somewhere permanently, because every time I seem to be recreating these pictures, right. So I have the first thing I said, okay, the Q star is somewhere there, right, I make a mistake, right. So and then I have this guy, right, so it is possible for me to make an error, right, and then the other case was, okay, the true Q was somewhere here, so it is possible for me to make a mistake, right. This third case says no, none of this really need to happen, right, the true Q stars could be well within the bounds, right, but given the current uncertainty I have in my Q of I, right, so the true means are not so far apart, right, this uncertainty cannot overwhelm it, right, the true means are actually within the uncertainty, therefore I could still make a mistake. So the first condition is not true, the second condition is not true, but I still made the mistake. Okay. So people have all of this expression, everyone has in their notebooks, people who are writing notes. People who are not writing notes, you have this seared in your memory, okay, because I am going to erase it, but I am going to need it again, okay. So I want all of you to remember this. Okay. So, let us look at one. So, I want to look at the probability that A star what did I do? Yeah. So, I want to bound that probability, right. So, can I do that? Remember I told you Sn is capital Q, I told you mu is Q star, right. So, we have that already, right. If you remember when I wrote down the Hofting Chernoff bounds, I told you the comparison, right. I told you that Sn is capital Q, mu is Q star. So, you have those there, right. So, essentially then your epsilon becomes Cm, right, and my bound is e power minus 2 epsilon squared n, right, and what is C in? So, it is 2 ln n by s squared plug it in, simplify it and tell me what is the answer. So, what is your n there? Now, what is the n that you have to plug into the expression? Yes. This is where the thing became a little messy, because the paper uses S as the, I mean they introduce an additional notation, right, but I did not use that and tried to use the T star T A star notation itself. So, it becomes T A star of S, that is the thing that you have to plug in. Okay. So, simplify it and tell me what is the answer. So, I plug in T A star of S here, M here, right, and then I have to square it, basically that is my epsilon that gets squared, right. So, my T A star of S and my T A star of S get cancelled, right, I will get ln M, come on, after all that we have done so far you could do this simplification easily enough, just substitute this into that and then cancel things out and tell me what is happening. Huh? 1 by m power 4, right. So, essentially this will be less than or equal to okay. So, what about the second term? Huh? Okay, what about the third term? Okay, here is where we are going to use our mysterious L. Right, what did I introduce L for? I said that, hey, I have done so many number of trials already, okay. I am only looking at these events after that many number of times I have taken arm I, right. So I am going to make the following statement. If I have taken sufficient number of trials initially, okay, if you have taken sufficient number of pulls of arm I initially, this event will never happen. That is what I am claiming, right. It is rather easy to see, right. So what do we have? We have Q star A star minus Q star I minus 2 C M okay. Right. So essentially I am saying that my TISI is at least this much, right. So that is what this means, right. If I say L is equal to this much, that means the number of times I have taken arm I is at least this much. If you remember, my SI summation starts from L, right. I consider SI only from L. So if I say L is this, so that means my TISI is at least this much, correct. Go and plug this into my CNS expression, right. So if my S is this much, at least this much, so what do I get? I get 2 by 8 ln m, and my delta I squared will go up. So ln m will get cancelled, right. So 2 by 8 will become 1 by 4, that is half into delta I, right. So half and half 2 will get cancelled, I will essentially get delta I, right. So this expression will become right. And what is this equal to? So for any value of L greater than this quantity will be greater than 0, that means this inequality will never hold, correct. Do people see that? You want me to do that again? Yes? Okay. So I am saying L is going to be at least this much. So then if you remember, my TISI, that the SI summation is starting from L. I am assuming that at least L times I have taken this already, right. So I am assuming I have taken this L times already. So what I will do is I will plug this value for the number of times I have taken this already, right, this value. So I will plug in 8 ln m, right. This is C m comma S, right. So in this case look at this, the expression is m comma this. So this will be ln m, right. I am plugging in here instead of S, I will plug in 8 times ln m divided by delta I squared, right. Ln m will get cancelled, So 2 by 8 will become 1 by 4 and divide by delta I squared will go up, right. So I will basically get root of delta I squared by 4 which is delta I by 2, right. So I will come and plug in delta I by 2 here, 2 and 2 will get cancelled, I will essentially end up getting delta I here. So that is what I have written here. So and by definition of delta I, this expression is 0, right, and for values larger, I mean if I take the ai more times, then this will essentially become greater than 0 and therefore that inequality that I wanted will never hold. If I have taken L at least, if I have taken action I at least L number of times where L is given by that expression, the third condition will never hold. Okay, so the probability of the third condition holding is 0 if L is greater than this, right. So now what happens, so the probability of this whole thing happening is upper bounded by just 2 times this probability, right, just add these events up, right. So we are still not done. Where are we? So we are bounding the expected value of that thing, right. So we have expected value of so I am going to ask you to write this out here, okay. So this is lesser than or equal to 8 ln n by delta I squared because that is L plus the summation terms that we had earlier, right, and I am substituting a specific value for L here, okay. Then what will be the internal term here? Remember we had this random variable which could take values of 1 or 0. So what is the expected value of the random variable is just the probability of it being 1, right. So there are only 2 of those things, right. So the probability of this event plus the probability of this event, right, that is basically it, right. So I am not writing down this because these expressions are going to take a long thing. So probability of this event plus the probability of that event. So in which our case is just m minus 4, m power minus 4, m power minus 4, that is essentially right. So is that clear? So you see how that came about, right. So here this was a random variable, right. Now once I took the expectation, so I can replace that random variable with the probability of it being 1, that will be the expectation of that random variable, okay. Is it fine? So I replace that with the probability of it being 1 is upper bounded by m minus 4 and that is basically it, okay, great. So this summation, okay, I am going to declare it to converge to 1 plus pi squared by 3. Okay, I mean you can, it is a little involved thing but it is pure algebra guys, I mean you can work it out, okay. Or I mean it is just a standard relation, you can look it up also, right. So that is basically what we have. So this is, you can kind of see, right, this is going to, because it is going to be a diminishing sum, so it is going to converge to a limit, right. And so what is really interesting is this part, right, it is some constant, whatever is it that it converges to, it is not really of interest, not really of great interest. What is really of interest is this 8 ln n by delta I, right, because this is the one where you are going to get messed up a lot, because it has the ln n term, right, and it also has your delta I squared, right, but this is only the expected value of tin, right. You have to multiply it by delta I to get the total regret, and you have to sum over all I, right. So that is essentially the thing that we have finally, that expression that I erased here, that is what you will end up with. That is why I said keep that in your mind, because that is the final expression you are going to end up with, right. This is for each arm, this is for one suboptimal arm, right. This is the total number of times you have played it, right. That is all we have derived now. So the regret due to that suboptimal arm will be delta I times this number. So that is why the delta I squared goes to delta I in the denominator in the original expression. If you flip back and you look at the original expression, we had a delta I here, and we also had a 1 plus pi squared by 3 into delta I, but this is for one arm. So you have to do this for all the suboptimal arms basically. That is why your summation is over all I which is not optimal. Okay, great. So this is that we are done with UCB, and we have shown that UCB's regret is bounded, and what is the nice thing we have shown here is that the regret grows as ln n, right, and that is a result from the 80s which tells us that you cannot have a regret optimizing algorithm that does better than ln n, right. What you can try to improve on is the 8, right. This is also impossible to get rid of, the delta I is also impossible to get rid of. If you can't say that I mean if arms are close in reward, right, it becomes hard to eliminate the bad arms, right. If they are far away in reward, then you can quickly figure out which are the bad arms, but if arms are close in reward, it becomes harder to figure out. So those things are always there. So those are essential components to it. So basically people fiddle around with that 8, okay, and yeah, so that is essentially a lot of work that happens in regret optimality. So I will have to stop here because we have reached 5 o'clock. I do not know if how many of you noticed it. So if you hadn't, I will take that as I kept you successfully engrossed, but if people were just biding their time to leave, well, I apologize for keeping you here for so long, but I needed to finish this, right. I could not have stopped halfway through and start in the next class with 3 summations or something, right. So the next class, right, we will look at the last optimality criterion I was talking about, which was pack optimality, okay.